Okay, gentlemen, we start with the study of excitation systems. Today, we shall cover the control and protective functions. The control and protective functions provided in the excitation systems are AC and DC regulators, load compensation, under excitation limiter, over excitation limiter, and field sorting circuits. We shall also study today the types of excitation systems, types of excitation systems. Briefly, as you all know, the control and protective functions are required to achieve the desired performance of the generator and power system. We have excitation control, excitation limiting, and excitation protection. There are three different functions are there: control, protection, and limiting. Here, this is the most general block diagram of the excitation system, which shows the different control, protection, and limiting functions. Now, let us just look at here in this diagram. This is our exciter. Just associated with the exciter is a field sorting circuit. We will discuss the need for the field sorting circuit, and the output of the exciter is given to the field winding of the generator, right, and it is connected to the system. Now, the different control and protection functions are here. One is the excitation system stabilizer circuits. You just see it here, the excitation system stabilizer circuit. Here what we do is that we take the signal from the terminal of the exciter, and this is fed to AC regulator. Then there are three limiting circuits. One is the over excitation limiter, under excitation limiter, and volts per hertz limiter, and protection. Now, this say over excitation limiter takes its input signal from the output of the exciter and again feeds this to the AC regulator. Under excitation limiter gets its signal from the terminal of the generator and again operates through the AC regulator. Voltage per hertz limiter as well as the protection, right, this also gets its signal from the generator terminals, okay, and it feeds to the AC regulator. Okay. Earlier we have seen that the control functions start like the voltage sensing and load compensation, that also acts through the regulator, AC regulator. We have power system stabilizer, that also acts through the AC regulator, right. And in addition to the AC regulator, because in the previous block diagram I had shown only one regulator. Now, here we have shown two regulators, one is called DC regulator, another is called AC regulator. The DC regulator has a very limited role. Most of the time only the AC regulator which functions, okay. But when the AC regulator is taken out because of some or the other reasons, in that case the DC regulator comes in or is put into service. DC regulator instead of controlling the terminal voltage of the generator, it basically regulates the output of the exciter. output of the exciter is a DC voltage, and it is DC voltage which is regulated by the DC regulator. While the AC regulator is concerned, it has all these multiple functions: control, protection, limiter. All these functions are through AC regulator. Now, we will briefly discuss these components. Before I talk about the components separately, let me mention here that in any excitation system you may have all these functions or some of these functions. It is not necessary that any given excitation system will have all these functions associated with it. Depending upon the requirement, some functions may be present, some functions may not be incorporated. Now, let us just discuss briefly AC and DC regulators. The basic function of the AC regulator is to maintain stator voltage, right. That is the output of the synchronous generator. The DC regulator holds constant the generator field voltage and is also referred to as manual control. Okay. Now, in any excitation system, we require the excitation system stabilization, right, and the simple block diagram of the excitation system stabilizer is shown here. This block represents the exciter and AVR, okay, and the output of this exciter is the DC voltage we represent by EFD, the voltage applied to the field winding of the synchronous generator. Then, in order to have stable performance of this exciter and AVR, the simplest stabilization circuit which is used is derivative feedback, and this derivative feedback is achieved through this transfer function. We will discuss the details about this derivative feedback when I talk about the models of components of the excitation system, because after we discuss the basic functions we will go to the modeling, and while talking about the modeling we will first talk about the models of various components and then the excitation system model as a whole, right. Now, this feedback block we can see here has the transfer function of this form S kf upon divided by 1 plus S times Tf, right. Now, this denominator represents the time delay which is provided, and the numerator we have actually this function S kf. The S stands for d by dt, and therefore, it provides a derivative feedback signal, and by properly adjusting the values of these parameters kf and Tf, we can achieve the desired dynamic performance of the exciter. Okay. The next component is the load compensation. This load compensation here we derive a voltage Vc which is obtained by adding a voltage drop Rc plus j times Xc into It to terminal voltage, that is to the terminal voltage of the synchronous generator. You add a voltage drop which is represented by this term, that is a complex number. Rc plus j times Xc is a complex number. Multiply this by the terminal current, right, and you perform this phasor addition and then obtain a quantity which is proportional to the magnitude of this quantity, that is Vt Et plus RC plus J times XC into IT. This is a phasor, it is a complex number. Find the magnitude of this, and therefore Vc is the a scalar quantity, right, and this quantity, the Vc, represent the terminal voltage plus voltage drop in the complex impedance, or in the impedance RC plus J times XC. Now, in the practical system, the voltage Vc is derived by this basic schematic diagram, using this schematic diagram. From the terminal voltage, you put a potential transformer and get a voltage signal which is proportional to the terminal voltage. In the output of the synchronous generator, right, you put current transformer and extract a current proportional to the load current, right. Now, these two quantities, that is, this is a quantity proportional to the terminal voltage, here is the quantity which is proportional to the terminal current. Okay. These are fed to a block diagram which is called load compensator, right. It has a real term RC and a imaginary term which is represented by XC. That is, this can be visualized as if you have a impedance of the value of RC plus J times XC, right. Practically it will not be an impedance, it is only actually a complex number which can be used actually to derive a voltage signal Vc. Now, this voltage signal is fed to the regulator, right, and ultimately the field current of the synchronous generator is regulated like this. In case we do not want any load compensation, then the RC and XC will be set to 0. Okay. So, that what you regulate will be the terminal voltage of the synchronous generator. Okay. Now, suppose if I take the RC and XC positive, then the voltage which we regulate is not the terminal voltage, but what we regulate is the voltage which is somewhere inside the synchronous generator, because here this there is from the what's up some voltage generator inside the synchronous generator, right, that voltage drops and we get a terminal voltage here. Therefore, what we get by setting RC and XC positive, the voltage drop across the compensator is added to the terminal voltage. Okay. The compensator regulates the voltage at a point within the generator and thus provide the voltage drop. Now, this is particularly required when you have two generators, right, which are connected in parallel, and we want to do the reactive load sharing, right. Now, the reactive load sharing by the two generators will depend upon the internal voltage which is generated, and therefore, here we are trying to regulate the internal voltage. In case you put RC and XC negative, right, because as I told you that you can make the real term negative, reactive term also can be made negative. The compensator regulates voltage at a point beyond the machine terminals, that is terminal voltage is ET, right. From this ET you are subtracting some voltage drop, and therefore, basically you are trying to regulate a voltage somewhere beyond the terminal voltage of the machine, right. Now, this type of compensator is required where you parallel the two generators having individual transformers. There is the terminal voltage, a generator, its own generator transformer, a generator its own generator transformer, and then they are parallel on the high voltage side. Next component is the under excitation limiter. Now, the under excitation limiter means actually that in case the excitation current in the field winding of the synchronous generator goes below a certain value, then this type of operation is not permissible. That is, we should not reduce the field winding current below a certain set value. The basic reason is here, the under excitation limiter is intended to prevent reduction of generator excitation to a level where the small signal stability limit or the stator core and region heating limit is exceeded. Now, these details actually one has to look into the capability chart of the synchronous generator, where if the excitation becomes very low, right, then the small signal stability limit is evaluated. Okay. And there are different names which are given to this under excitation limiter. When you look the operation of the synchronous generator in the PQ plane, right. Now, this is the P axis, that is real power output. This is the reactive power output. When this generator is over excited, it supplies positive Q, and when it is under excited, it supplies negative Q. And the operating limits, this is the under excitation limiter which is shown here. The under excitation limiter setting is done so that it is coordinated with respect to the small signal stability limit. That is, this curve shows the small scale of the small signal stability limit. That is, in case you operate in this portion of the PQ plane, the system is stable for small perturbations. If you operate somewhere in this region, that is on this side of this characteristic, system becomes unstable, right. The small signal stability will be studying separately. Okay. Now, keeping some margin, the under excitation limit is set like this. There is also one characteristic which is also provided, it is called the loss of excitation relay. That is, whenever the synchronous machine loses its excitation, then there is a relay which is used to protect the synchronous generator, right. The characteristic of the loss of excitation relay is also shown here in this diagram. This is the characteristic of the loss of excitation relay, right. Therefore, these three characteristics actually, that when you set the under excitation limiter settings, okay, these have to be coordinated with respect to the small signal stability limit and loss of excitation relay characteristic. Okay. And we have to see at the same time that both these characteristics are outside the setting of the under excitation limiter. This margin whatsoever you provide, that is a safety margin. The next limiter is the over excitation limiter. The purpose of over excitation limiter is to protect the system from overheating due to prolonged field overcurrent. In case the field current is more than the permissible or the rating of the synchronous generator, right, and if that current is more than the rated value for a prolonged time, then naturally because of overheating of the field winding may get damaged, right. Therefore, the purpose of the over excitation limiter is to protect the system from overheating due to prolonged field overcurrent. This limiter is also referred to as the maximum excitation limiter, whether you call it over excitation limiter or maximum excitation limiter. There are two different names which are used in the literature. the overexcitation limiting function typically detects the high field current condition. That is it has to detect the high field current condition, and after a certain time delay acts through the AC regulator to ramp down the excitation to the present value. In case the current in the field circuit is more, it is detected, then since actually the over excitation is permitted for some small amount of time, okay, then this limiter what it will do is it will ramp down, it will bring down the field current and bring it to the rated value. Now, this graph shows the characteristic of the overexcitation limiting. That is, on this axis we have marked what is marked is generator field voltage per unit of rated value. That is, you start from the rated value is 1, 1.1, 1.2, 1.3, 1.4, 1.5 like this. And on this y axis we are putting the time in seconds, right. The times are 30 seconds, 60 seconds, 90 seconds and 120 seconds. This gives you the range over which actually the excitation system overloading is permitted or over excitation is permitted. Now, this characteristic A, which you can see it here, right. This characteristic shows the field thermal capability. You can easily understand actually that suppose the generator field voltage per unit of the rated value. Now, here the whatsoever voltage you apply, right, the corresponding current will flow, because under steady state conditions the field current is equal to the field voltage divided by the field resistance, right. And therefore, this generator field voltage per unit of rated value also represents the corresponding field current. And you can easily see that as this value increases, the time for which it can be permitted is decreasing. This is practically this type of characteristic, inverse characteristic. And the characteristic of the overexcitation limiter is to be coordinated with respect to the field thermal capability. You have to always keep some margin, and therefore, the characteristic of the overexcitation limiting is given by giving some margin, in the sense that suppose I take this example here. For example, if you let us say field voltage is 1.3 per unit, okay, then it can withstand this over voltage for this much time, right. But keeping some margin, our limiter will operate in a time which is less than the upper limit, right. And therefore, this is the margin which is provided, a safety margin you can call it. Now, this table shows the time in seconds versus the field voltage oblique current in percent of rated value, right. That is, from this graph we have just picked up some values, and that shows actually that if the applied voltage is 2.08 per unit or 208% of the rated value, it can withstand for 10 seconds. If it is 146%, right, it can withstand for 30 seconds. If it is 25% more than the rated value, it can withstand for 60 seconds, and 12% more than the rated value can withstand for about 2 minutes, is 120 seconds. Now, this is the thermal characteristic of a round rotor generator, turbo generator, round rotor. because these characteristics are going to be different for different machines. For typical machine, this has to be provided by the manufacturer. Then the next important limiter and the protection function is the voltage per hertz limiter. Voltage per hertz limiter. Now, here we all know that the flux produced in the core is function of the terminal voltage. That is, we have a standard EMF equation, right. Therefore, the voltage is related to the flux and the frequency. Okay. Now, suppose you are operating and at a situation where frequency drops and voltage rises, voltage becomes more, frequency becomes less. Okay. It means V by F becomes more. Under that situation, the operating flux will become more, it will increase, and when the flux increases, it will cause additional core losses, right. And therefore, there is a necessity to provide the protections against such eventuality. One simple example is that when generator is disconnected from the load, or actually the load is thrown off, at that time there is a tendency for the machine to speed up, and the frequency rises, voltage also rises, right. And in case the V by F ratio is beyond a certain permissible value, then this limiter will come into action and take necessary action, right. Therefore, basically this is provided to safeguard the generator from the excessive magnetic flux. Now, not only the generator, actually the transformer which is connected to the generator is also affected when the V by F ratio is more than certain value. Now, the ratio of per unit voltage and per unit frequency, referred to as the volts per hertz, is readily measurable quantity that is proportional to the magnetic flux, that is V by F ratio. But here the ratio is taken, the voltage is expressed in per unit, frequency also is expressed in per unit, right, and that ratio V by F, not the absolute value. This per unit ratio reflects the overfluxing capacity of the synchronous generator. This is also called overfluxing. Here this table shows the voltage per hertz in per unit. You can see it is this is 1.051. I think this is slightly mistake, must have been. No, this is 1.25, 1.2, 1.15. This may be 1.1. This is 1.1. Make a correction. 1.1, 1.05. Now, here damage time of the machines, right? Damage times are given in minutes here. The time is expressed in minutes. Instead of putting in seconds, here it is in minutes. Now, damage time for generator and transformer are separately mentioned here. That is, in case this ratio V by hertz or voltage per hertz is 1.25, the generator can withstand this for 0.2 minutes. If it is 20% more, then for 1 minute. It is if 15%, it is about 6 minutes. It is 10%, it can withstand for 20 minutes, and if it is 5% more than infinite, this is the capability. That is, if this V by F ratio, right, in per unit is 1.05, then there is nothing to worry. For the transformer, the permissible times are more. You can easily see here that instead of 0.2 here it is 1 minute. For 20% V by F, right, 1.2 times V by F is 5 minutes, 1.15 is 20 minutes, and 10% is infinite, right. Therefore, based upon this permissible values, right, the setting of the limiter or the voltage per hertz limiter settings are decided. Now, this field shorting is a very special provision which is provided on the synchronous generator. Especially when we have the excitation systems where we use the rectifiers to supply the field current, because you will see that we have two categories of excitation systems. One is AC excitation system, where the output of the AC exciter is rectified and given to the field winding. Similarly, the static excitation system, right, we take the terminal voltage, terminal current, rectify and give the field current to the synchronous generator, right. In these two types of excitation system, we cannot make the field current to reverse, because rectifiers are provided, therefore, the field current cannot reverse. And under certain situation, it is desirable to allow the current to flow in the reverse direction, particularly during pole slipping or during short circuit conditions, where in the stator carries the DC component whenever the fault occurs at the terminal of synchronous generator, right. The voltages which are produced in the field winding of the synchronous generator, right, if they try to drive the current in the reverse direction. In case you do not have this provision, then the voltage produced will be very high, which may damage the field winding of the synchronous generator. And therefore, there are two different circuits which are provided. One is that across the field winding you put a thyristor control field discharge resistance, right. That is, this resistance is always provided actually along with the excitation system, right. And the moment actually the voltage across the field winding becomes more than a certain set value, then this thyristor is switched on, right, and it will allow the current to flow in the reverse direction, right. Otherwise, actually the field current is flowing, say, in this direction, okay, and this thyristor is off. Therefore, there is no current flowing here, and this field current cannot reverse, it cannot flow in the reverse direction, it flow only in this direction. Now, suppose the due to some faults on the terminal of synchronous generator, right, in the field winding some voltages are produced which have this type of polarity, and in case actually we provide a path for the reverse current to flow, then this voltage will not go beyond a particular limit. If this path is not provided, then this voltage becomes high and it is dangerous to the life of the synchronous generator field winding. Another arrangement is that make use of varistor, which is a non-linear resistance. When the voltage across this circuit is below a set value or some less value, then it offers infinite resistance, and when voltage goes beyond certain value, it offers low resistance, and therefore it allows the field current to flow in the negative direction, right. They are the two arrangements which are provided as a special protection for the field winding of the synchronous generator. Therefore, with this I can say that we have discussed the various control and protection functions provided on the synchronous generator excitation system. It is not synchronous, it is synchronous generator excitation system. Now, we will briefly talk about the different types of excitation systems. Excitation systems are broadly classified into three categories: DC excitation system, AC excitation system, and static excitation systems. the excitation power required for a synchronous generator is of the order of 2 to 3.5 kilowatt per megawatt rating of the machine or per MV rating of the machine. The DC excitation systems were the oldest of all the excitation systems, and the main limitation of DC excitation system is the amount of power which can be delivered, and the commutation is the main problem in the excitation system. The more the current to be delivered, more is the commutation problem. In 1960s, the DC excitation system has been superseded by AC excitation systems. In AC excitation systems, we have two different type of excitation systems, stationary rectifier systems and rotating rectifier systems. While in static excitation systems, we have different types of arrangements. One is the potential source control rectifier system, compound source rectifier system, and third is the compound control rectifier excitation system. Now, this figure shows the schematic diagram of a DC excitation system. The DC generator is the source of power for supplying DC current to the field winding of the synchronous generator. If you see here, then this represents the DC exciter, this is the armature, this is the field winding. The output of the DC generator feeds the field winding of the synchronous generator through slip rings. The DC exciter may be driven by the turbine shaft or by a separate motor also, and this may be a self excited or a separately excited machine. The voltage regulators may be a rheostatic type or the magnetic amplifier or amplidyne type, and this type of excitation systems are still existing in many of the power plants, and therefore, modeling of this DC excitation system is also important. We shall discuss the modeling of DC excitation system separately. Now, this diagram shows the AC excitation system. In AC excitation system, the field power is obtained from AC exciter. The AC exciter is a AC generator, and this AC generator may be driven again by a separate motor or by a shaft of the turbine. Generally, this AC exciter is driven by the turbine shaft itself. Now, here in this arrangement, we are using the stationary diode arrangement, that is the output of the AC exciter is rectified with the help of stationary diodes, and the DC current is fed to the field winding of the synchronous generator through slip rings. Now, here when we use the non-control rectifiers, then the output of the exciter is regulated by controlling the field current of the AC exciter. Therefore, if you see here in this diagram, then the AC regulator acts to control the firing angle of the control rectifier, and it regulates the output of the AC exciter. The another arrangement which is possible is that we use stationary control rectifier. That is, instead of using the stationary uncontrolled rectifiers as is shown here, we can use the stationary controlled rectifiers. Other arrangement is exactly the same as in the previous case. Now, once we use this stationary control rectifier, then the output of the excitation is adjusted or controlled by controlling the firing angle of the control rectifier here itself. That is, this AC regulator will directly control the firing angle of the stationary control rectifier. And this AC exciter provides AC output, and the control output is obtained by rectifying the this DC AC output to DC, but in a controlled fashion. The other arrangement is exactly similar to what we discussed in the earlier case. Now, in these two arrangements which we discussed for the AC exciters, the armature of the AC exciter is stationary and field system is rotating, while the field of the synchronous generator is getting its supply through slip rings. Therefore, in this AC exciter we have still the presence of slip rings, and the another alternative arrangement which has been used is where we do not make use of slip rings, and that is called the brushless excitation system. In brushless excitation system, we have AC exciter, uncontrolled rectifier, and the output of the AC exciter is fed to the field winding. Now, the armature of the alternator or the armature of the AC exciter is made rotating, right. The rectifiers are also rotating, the field system is rotating, and therefore, we can see here that armature of the AC exciter, the rectifiers and the field system, they are rotating and they are connected rigidly without having any slipping contact. The excitation of the AC exciter, how do we provide the excitation for the AC exciter? The AC exciter excitation is provided by using a pilot exciter. This pilot exciter has the permanent magnet field system, right, and the armature is stationary. Now, in this arrangement, the rectifiers are not accessible to us because they are rotating, and therefore, we cannot have controlled rectifiers in the brushless excitation system. The control of the excitation system is achieved by controlling the field current of the AC exciter. That is, the AC exciter gets its field current through a controlled rectifier. That is the AC regulator. This is the AC regulator. This AC regulator acts on the control rectifier which are provided here, and we supply the control field current in the AC exciter. And in this arrangement, we will be in a position to control the output of the exciter by controlling the field current of the AC exciter. However, another problem is that the field voltage and field current cannot be measured directly. That is, since this field system is rotating, rectifiers are rotating, and therefore, there is no way directly to measure the field current directly. And therefore, if we want to get the information about how much field current is flowing, this can be obtained indirectly by measuring the field current of the pilot exciter, and not the AC field current of the AC exciter, that is the output of the pilot exciter. The major advantage of this type of excitation system is that we do not have slip rings, and once we do not have slip rings, right, the problem of maintenance of the slip rings, the carbon brushes, flashovers, all these things are eliminated. The excitation systems, whether you use a stationary rectifier excitation system or brushless excitation system, the dynamic performance of these two systems have been found to be practically identical. Therefore, from the point of view of performance, there is no special choice whether we choose stationary rectifier excitation system or brushless excitation system. Both these arrangements provide the similar dynamic performance. Now, we briefly talk about the static excitation system, the static excitation system. Now, this figure shows the schematic diagram of a static excitation system. In static excitation system, the excitation power is derived from the terminal of the synchronous generator or from the auxiliary bus of the power plant. Now, in this arrangement, we make use of this exciter transformer. The input to the exciter transformer comes from the terminal of the synchronous generator itself, and output of this exciter transformer is rectified using the control rectifier, and this output is fed to the field winding of the main generator or main synchronous generator through slip rings. Therefore, in this static excitation system we do require the slip rings. The control is the output of the excitation system is controlled by controlling the firing angle of the control rectifiers. That is, the AC regulator directly acts, this is the AC regulator, this AC regulator directly acts on control rectifiers, and we get the regulated current in the field circuit of the synchronous generator. Now, one major advantage of the static excitation system is that we do not have any rotating part so far the excitation or the excitation system is concerned. Another thing is that the response time of this static excitation system is very low, that is, they are very fast. There is one more arrangement of static excitation system. Now, here this is the main generator. To get the required field current, instead of making use of only potential or power potential transformer to get the required field current, we make use of an arrangement which is called compound source rectifier excitation system. Here the field current in the main generator is made function of the terminal voltage of the synchronous generator and the load current. Therefore, if you see here in this arrangement, then we make use of a transformer which is called saturable current transformer. This saturable current transformer is connected in the neutral circuit of the main alternator. Then we can obtain a quantity proportional to the load current, we can obtain a quantity proportional to the terminal voltage. These two quantities, that is terminal voltage and load current, they are appropriately combined, and we get an output which is fed to the power rectifier, and the output of the power rectifier field gives the field current to the synchronous machine field winding. Now, the major advantage of this is that whenever suppose there is a fault which occurs at the terminal of the synchronous generator, if we use a simple static excitation system using the exciter transformer only, then when the three phase fault occurs or some sort of fault occurs at the synchronous machine terminals, right, then the voltage available to this transformer becomes 0 or it dips, then this will affect the field current of the excitation system. Now, in this arrangement, when the voltage at the terminal of the synchronous generator dips, but simultaneously the current becomes high, right. So, that we will be in a position to maintain the field current even under the disturbance conditions. With this I will conclude that what we have discussed today is that the various control, protection and limiting functions of the excitation system and different type of excitation systems. We have also seen the limitations of DC excitation system, the merits of AC excitation system and particularly the merits of brushless excitation system. Today in major power plants, the excitation systems are either AC excitation systems or static excitation systems. Thank you.